So when I went, to try to explain this, people weren't understanding that the opposite of fragile isn't robust. It's not solid. It is not the opposite of fragile. The opposite of this is not the straight line. It's not a payoff, where you end up unharmed. You agree? If I'm sending a package to, say, Mongolia interior, all right, and the package is fragile, what do I write on it? Fragile, all right, okay. If the package is robust, what do you write on it? Nothing. So if the package wants volatility, wants to be harmed, wants something, wants stressors, wants disorder, wants earthquakes, all right, it's not the same as robust. It would be something on which you'd write, please mishandle, I am anti-fragile. It's the opposite of fragile. So the opposite of fragile is not something that is robust or something solid. It's something that wants disorder. And guess what? There's something called the cluster. And if you like one, you like them all. Uncertainty, variability, imperfect, incomplete knowledge, chance, chaos. These, if you benefit from all of these, you are classified as anti-fragile, and it's very similar to someone who owns an option. So we're going to talk about how you guys can milk randomness, because that's what you do in California, all right? And we're going to be a little more technical and a little more rigorous in the way we analyze an option payoff. So there are things now, let's view the world in three categories. There's the fragile, like this computer. You pour water on it, it's gone, all right? You understand? And now we have to give a lecture maneuvering with a mouse and maneuvering so it doesn't blow up, and hoping it doesn't blow up before the end of this lecture, all right? That's a fragile, okay? That's the definition. There's a robust, you hammer it, nothing happens, but doesn't benefit from it. And there's the anti-fragile that likes disorder and benefits from disorder and benefits from error. So it happened that now we can identify the fragile. There's a method to figure out what is fragile, and there's a method to figure out what is anti-fragile. How? Very simple. Something related to convexity. Let me explain what I mean by convexity or concavity, okay? If I jump, I am fragile, my body is fragile, okay? If I jump 10 meters, what would happen to me? You guys are engineers and smart people, you would know. What would happen to me? Sorry? I die. I'm going to say it. This is, you die. Your hospital here won't be any good, right? You die when you fall 10 meters. But if I fall 10 times 1 meter, what would happen to me? Nothing. It means that every additional meter harms me more than the previous one. No? Everything fragile, we saw it in time series space. But if you look at it as a response, everything fragile has to have accelerating harm at some point. And we can actually show that everything that has accelerating harm doesn't like volatility. And the opposite of it is something that has accelerating benefits. The nonlinear is harm more. You see this accelerating harm is harm a lot more than the linear. And visibly, the linear, for small variation, show more response than the nonlinear. This is easier to understand if you look at it this way. You saw that the harm I get from hitting the floor, okay, it has to be nonlinear for me to be harmed at 10 meters, but not to be harmed at 10 times 1 meter. You agree? Okay. It has to be that way because walking, from on campus would kill you otherwise. Because being harmed by that large, but you get the, if the thing were linear, you'd be killed. So harm for anything that has not been broken has to be in a nonlinear. The coffee cup sees thousands of hits, very small intensity, like very small pounds per inch hits. It doesn't really care. But one big hit and it breaks. So things that are fragile have to be nonlinear. And this is what's central about this idea. You have to be accelerating in harm. Another example is, look at the world around us, okay? If we were linear to harm, we were blown up a long time ago. The world has 3 to 4 million earthquakes every year, low intensity on a Geiger scale, you see? It would be like a Fukushima every few minutes if the harm were linear, but it's not, you see? Yeah. So this is quite central because now we can figure out what is fragile from nonlinear and look at its opposite. Simply, we have the following. If you have more gain, say if the market goes up 10%, you make more money than if the market went down 10%, then you lose if the market went down 10%, you're convex, you see? And otherwise you're concave. The best way to figure it out is with this. This is convex, this is concave. If you want to remember, this is convex. And this is concave. Okay? So if you look at the payoff of the convex, you make more, then you lose. You're here, you make more, then you lose here for an equivalent one. Or you make more the second time than you make the first time. If the market goes up 20%, you make more than twice if the market went up 10%. If you are in that situation, then you like volatility. If you're in that situation, then you are like benefiting from randomness, what I call the disorder brothers. Uncertainty, all these things. Let me take 1 or 2 questions here before continuing. And as you're asking the question, I can see if I can fix the computer. Yes?
Are you considering only the sloping upside of the convex curve? Because it seems to me that on the other side of your smiley face, you would lose...
No, if it's on the increasing, it has to be increasing, but you're not going to be here also. I mean, it's not going to be harmed. Here, this is f of x, and this is x. And if you're here, you see, or it's decreasing, but not very, at a decreasing rate, you see. For the increasing, all right, you make more than you lose. And for the decreasing, it slows down.